we will introduce something that is known as the fundamental group. If you have previous experience with the fundamental group, then this lecture will be sort of a review of sorts. And this lecture will have a lot of material in it, more so than the other lectures. Basically, what we're saying is we're going to cover a lot of stuff fairly quickly, and then the lectures that follow after that will go at a more reasonable pace. I'm just assuming that the audience is probably familiar with this, or you've seen it on some kind of level. So this is mostly a review. But even if you've never seen the fundamental group, it will contain all of the information that you need. Of course, if you have experience with the fundamental group, that is only a benefit, but it's going to be self-contained. Now, before we give the definition of the fundamental group, I just want to give you the idea of what it is. So this is sort of we can say the motivation for what this is. So X, this is going to be a topological space. Every time we say space, we will mean topological space, unless we mean otherwise. And as we said on the first lecture, if you're more comfortable with metric spaces, you can just assume that X is a metric space. Or even more concrete, you can just assume that X is some subset. It's some kind of region within Euclidean space. And you're going to pick a point in X. So we're assuming that X is not empty. Otherwise, this is not very interesting. And this is how it's going to be defined. So pi 1 of X comma P. This is called the fundamental group of X at the point P. And what is this? So this is going to be, by definition, so we're going to make this rigorous. That's sort of the point of the lecture, to make this rigorous. But I want to give you at least the intuition. This is going to be, you can say, closed loops at P that are within X. And really, these are not going to be a closed loop. These are really going to be equivalence classes of closed loops at P within X. So let me show you a picture, and then we'll make it rigorous afterwards. So let's say that X is the annulus. So the annulus is something that looks like this. It's two concentric circles, and then it's the region that's in between two concentric circles. And let's pick a point. It does not matter where you pick the point. Let's say this. So let's say this is our point P. So let's give an example of what we mean by a closed loop. So I'm going to draw this picture a little bit bigger. So here's an example of a closed loop. So here's our point P. So an example of a closed loop would be something that goes around like this. Okay, so let's call this alpha. So alpha is a closed loop at P. So it begins and ends at the same point. So that makes it closed. And it's it goes around in the loop. And let's say alpha goes around like this, counterclockwise. Now, another example of a closed loop is maybe, so here's our point P again. So maybe instead, alpha goes like this, or maybe to change the picture a little bit, let's say alpha, let's say it goes like this instead. It sort of perturbates a little bit as it goes around. It's still going counterclockwise, and let's call this beta. So beta is also a closed loop at P. And what we want to do is we want alpha and beta to be the same. Now, they're obviously not the same loop. You can see they're different loops, but we want to treat them as equivalent, right? So the mathematical term here is we talk about equivalence classes. You want to treat them as being equivalent objects. Even though they might not be the same, you want to treat them as equivalent objects. And the reason for this is because in topology, as we remarked, We do not care how big something is or how small something is. If you make slight, small deformations in your space, it should not really matter. So you can easily imagine taking all of these small little perturbations, and if it's made out of an elastic material, you can straighten them out so it looks just like alpha. So then you might feel, if you can do that, then that would mean that all loops should be the same. They should be equivalent, but that's not true. So let me give you some examples of where you get different types of loops. So going back to this picture again, let's say instead of going counterclockwise, we had something that went clockwise. Actually, these go clockwise, so something that went counterclockwise. So something that went like this. Let's call this gamma. So we would say that alpha and beta should be equivalent to each other, whereas alpha and gamma would not be equivalent to each other. It kind of makes sense that there is no way to go the other way around. The only way you can do it is if you were to somehow take this loop, lift it up, and flip it over. But the moment you lift up the loop to flip it over, you are leaving your space. You want to stay within the space. You want to stay within the annulus. So somehow that would be different. Another example of a loop that would be different is, let's say we had a picture that went like this. Let's say this was our point P, and let's say our loop went like that. Let's call that delta. Notice each of these loops, they go around the hole in the middle. This one does not go around the hole. And since this is topology, we can deform objects. We can move them around. And look what happens. We can keep on taking this loop delta, and we can keep on making it smaller. So basically, this over here is delta, and then we can kind of make it smaller, and we can make it smaller and smaller and smaller until it goes down to a point P. So sort of like we want to say that delta should be equivalent to a single point. It can be brought down to a single point. You cannot do it in the other examples, because if you look at this loop alpha, you cannot keep on shrinking alpha down to a point, because as you try to do it, you pass through the hole in the middle, and so you are leaving your space. You have to stay within your space. Your space sort of represents the universe and where all of these deformations take place. And that is essentially what the fundamental group is. X represents the space, P represents the point at which you're going to be drawing all of your loops, and it's not going to be loops at P. It's not going to be closed loops at P. It's going to be equivalence classes of loops at P. So you're going to sometimes regard two different looking loops as being the same if one can be continuously deformed into another one. Now, we are calling it a group, so that implies that there's also a way of multiplying two loops together, and you get some kind of group out of it as you do it. And we'll explain how loops are multiplied together afterwards, and then you would see how you get a group out of it. But for now, that's the definition of the fundamental group. Just some notation. The number 1 over here, it represents one dimension. And this is since loops are one-dimensional. There is something called pi 2 of xp, where instead of using loops, you're going to be using closed surfaces instead. But we're not going to go there. Later in the course, we will talk about homology groups. So we will talk about h1 of x, the first homology group. We'll talk about the second homology group, and we'll actually talk about all of them. The contrast would be that with the fundamental group, you have to select what you call the base point, and in homology groups that will follow afterwards later in the semester, there's not going to be a base point. We're not going to be talking about these. These are much more difficult to deal with. So we're not going to be talking about these. But we will talk about these. And this is the fundamental group. So this just indicates one dimension, and the pi over here stands for Poincaré. So pi makes a P sound, so this is Poincaré, named after Jules Henry Poincaré, who introduced this. So Poincaré is one of the great mathematicians in history. He's also a physicist, many other things, and he introduced this. He had this profound idea of looking at loops and recognizing that you get a group out of it. So in his honor, it is called the Poincaré group. Actually, there's a group in physics called the Poincare group. So you know you're a very intense mathematician when the same object, when the same term means multiple things at the same time. If you go to his Wikipedia page, then the list of things named after Poincare, it just keeps on going and going and going. It never stops. So that's just some terminology. So now we want to make this rigorous by defining, first of all, what does it mean to be a closed loop? What is an equivalence class? And then show how you get a group out of it and all those things. And then we'll look at some examples, some important examples that we should know. So let's remove this, and we'll begin with our first definition of today's lecture. So first I want to say what a path is. Let's make this definition. Let X be a topological space, or a metric space, or a subset of Euclidean space, however you prefer to interpret what we mean by a space. And P and Q are points in X. So we're assuming, of course, X is not empty, and it could happen that P is equal to Q. So they could be the same point. So for those of you who are comfortable thinking of Euclidean space, so let's say X sits inside R2, so then this would be some region in the plane, so this would be X. And then you take P and Q, so this would be P, this would be Q, and then that would mean P has two coordinates, P1 and P2, and Q has two coordinates, Q1 and Q2. Okay, so that's all what it means. So maybe this makes it a little bit more concrete. So you have 2 points in X and a path from P to Q in X. So we're going to define what is a path. Because when we talk about the fundamental group, we're going to be talking about closed paths, paths that return back to the very beginning. So a closed path from P to Q in X is a continuous map, or function if you prefer. Maybe some of you prefer to say function instead of map, but they're interchangeable. Is a continuous map from the closed unit interval into X. You can always assume that the interval is the unit interval by rescaling. So if something goes from 0 to 2, you can rescale it so it goes from 0 to 1 by like dividing by 2. If something goes from 1 to 2, you can retranslate it over by subtracting 1. So you can always make your interval go from 0 to 1. It's a continuous mapping with the property that f at 0 is P and f of 1 is Q. So here's a picture. So here's a nice picture of what's going on. So this is X. You have 2 points, P and you have Q. And this is a mapping. So you're mapping the unit interval. So this is the unit interval. So a nice flat unit interval. You're mapping this using F. So if you were to trace out the image of this, it will create, there'll be some kind of image, there'll be some kind of path that joins P and Q together. So it'll be some kind of path, and of course, it can cross over itself. That's perfectly fine. It'll be some kind of path. You often think of this as time. Time ranges from 0 to 1 unit. At time 0, you begin at P. At time 1, that's the terminal point, you end at Q. And this is what you trace out. So you have all of that. So that's the definition of a path. So this is the rigorous definition of a map. I also should say that it's assumed, I'm not even going to write this out, but when we write the interval from 0 to 1, we mean, of course, with the usual Euclidean topology. That's what is assumed here. So that's the definition of what it means to be a path from P to Q. So a closed path, and if P is equal to Q, then F is a closed path at P in X. So this is when the beginning point and the ending point are the same. Then you have a closed path. I know that at present, you might be wondering, why are we talking about paths in general as opposed to closed paths, because the fundamental group is defined using closed paths. It's just more convenient to define it in general to begin with, and then specialize to the closed paths. Now I want to give the next definition of something called a path-connected space. definition, we say a space X is path connected. And you can probably guess what this means if and only if for any two points, P and Q and X, and these can be any 2 points whatsoever, they do not have to be the same, we can find a path. So a path is a continuous function from 0, 1 into X, so that f of 0 is P and f of 1 is Q. So that's what we call a path-connected space. I want to give you a little bit of warning here that hopefully does not give any confusion, but this is really point set topology, which you do not need to know. But in point set topology, there's actually a difference between being connected and being path connected, as confusing as that may seem. And the simple explanation is being path connected, you're using the topology of X and the real number line, because you see this is a closed interval on the real number line. So the notion of being path connected, it uses both the topology in X and both the topology on the real line. They both play a role. Whereas the notion of being connected, it only uses the topology on X. So connected is something that's a little bit more general. And if that bothers you, just forget about it. For the purposes of this class, path connectedness is all we need. Connectedness is actually trickier to define. It's more confusing. It requires more understanding of point set topology. And I do not want to go there because we do not need to go there. And also, for the kind of spaces that we're going to be interested in, namely manifolds, we're going to be working with manifolds. For the kind of spaces that we're going to be interested in, these two notions will actually be equivalent to each other. So that's the definition of being path connected. And of course, if you want to see like a picture of something that's not path connected is if you have, let's say, a disk over here and you have a disk over there, and X represents both of those disks. I think you can agree with me that if this is P and this is Q, it's not possible to find the path from one to the other, right? You have to sort of leave your space. If you're wondering how to prove something like this, so here's like a hint. Maybe this would actually make like a good homework problem to prove rigorously, not by drawing pictures. It's always nice. So you see, when you're learning mathematics, it's nice to check things rigorously, things that seem obvious, and it is pretty obvious that it's not path connected. But it's nice to be able to check things rigorously because that's sort of the way you learn. You have very carefully stated definitions, and you want to be able to test those definitions against very basic examples that are clear to see how you would use it. So the basic hint, so the problem here is so here's a problem. You want to show X is not path connected. As I indicated in the first lecture, all of the problems and the entire course information will be posted in the video description once everything is completed. So once everything is finished, you'll see a PDF document or a link where you can get all of those problems. But for now, as the course is being prepared, you will unfortunately not have access to that at the moment. So you want to show that X is not path connected, and the hint here is you're going to assume X is path connected, and you're going to do something and contradict the intermediate value theorem from calculus. So it has something to do with the intermediate value theorem. Basically, so if you have, so the basic idea is that this is f of t, right? That's your path. You have a continuous function. So the idea would be that if you evaluate f at 0, you're over here, and if you do f of 1, you're over there. So let's say you look at the horizontal coordinate. The horizontal coordinate moves from there, and then it abruptly jumps, and it moves to over there. And that's supposed to contradict the intermediate value theorem. So that's the way you do it carefully. Okay, so now we want to get to the next idea, and that's what we want to say, that two paths one can be deformed into the other. And this one will use homotopy. So we actually talked about homotopy in the first lecture. So let's just review homotopy. Let's review homotopy. This was lecture 1. So say y and x are two spaces, two topological spaces. You'll probably notice it's a bit strange that I'm writing y first and x second, but you'll see why I'm doing that. And f from y to x and g from y to x are two, I'm just going to say maps. Unless otherwise stated, anytime you see maps in topology, you should always assume that they're continuous. So let's have that convention from this point on. So we have two continuous maps. So we say f and g are homotopic maps if and only if there is a homotopy map, let's call it H, that takes y cross 0, 1 into x, so that if you do H evaluated at, so as we remarked, this is, you're taking the product with y, Cartesian product with this interval. So if it makes you feel better, this is something in Euclidean space, right? So just imagine that y is a region in Euclidean space. So when you take the Cartesian product with 0, 1, you're just attaching one extra coordinate that ranges from 0 to 1. So the picture is you get some kind of cylinder out of that. So that if you do H of, so let's call this one S. Now you might be wondering, why am I calling it S and not T? Because when we talked about paths and they go from 0 to 1, I called it T. You'll see the reason for this. And let's say this variable, a point in y, let's call that, I do not want to call it, let's just call it P or something. So H of P comma S. So that H, when you set S is equal to 0, you get the first function. And when you set S is equal to 1, you get the second function. So intuitively, this homotopy mapping, it continuously deforms the first mapping into the second mapping. That's the basic idea of what's going on. And now we're going to, so now we're going to remove the word review, and this is going to be the definition of something that's very similar, but it's a little bit different. This is called path homotopy. Definition of path homotopy. So this is not the definition of homotopy. This is the definition of path homotopy. And essentially what we're going to do is we're going to make this y be the interval from 0 to 1, because we want to have a path. So let's change this up a little bit. So let's say x is a space. So let's say x is a space, and P and Q are points in x. And suppose we have two maps, but these are going to be paths. A path is a map from the interval from 0 to 1. So we're rather going to write it like this. So we have two paths, and suppose f from 0, 1 into x and g from 0, 1 into x are two paths from P to Q. And we're going to say f and g are, previously we say homotopic maps, but now we're going to say homotopic paths. We say f and g are, let's just say, path homotopic. If and only if there is a, instead of calling it a homotopy map, we call it a path homotopy map. If and only if there is a, so it's called a path homotopy map. Path homotopy map H. And now here's what's going to happen. Previously we had y, because y was our space. But now y was replaced itself by the interval from 0 to 1. So now you're going to have a path from 0, 1 cross 0, 1 into x. So we're going to call this one S and we're going to call this T. So the way I like to think about this is I think of the first one as representing time on the path, and the second one as representing interpolation between the two paths. If that's not clear, we're going to draw some pictures very soon, but let me just write it out what this is. So it's going to satisfy the same conditions as before, but there's going to be one extra condition. So that this is, of course, a continuous mapping. By the way, before we go on, this is a square. You can, if you want, you can imagine this as the horizontal coordinate goes from 0 to 1, and the vertical coordinate goes from 0 to 1. So this is the unit square. That's what that would be. That would be the product. So there's a path homotopy map with the properties that, with the following properties. If you do h of t comma 0, you get the first map, the first path, I should say. If you do h of t, if you set s is equal to 1, you get the second path. And now, if you set instead, so notice now, if we set s as 0 or s as 1, we get these two. And now if you set t as 0 and t as 1, then you're getting the endpoints. H of 0s should always be p, and h of 1s should always be q. So this is the extra condition. So this over here, this is the extra condition for path homotopy. This condition is not present when you talk about homotopy in general. It would not make sense for an arbitrary topological space Y, because for an arbitrary topological space Y, there is no time 0 and time 1. That would not make sense. But it does make sense when you talk about paths. So here's the picture for what we're saying. The picture is we have some kind of space X, and we have 2 points. We have a point P and we have a point Q. And what's happening here is when S is 0, we get one path. We get some kind of path out of this. This is F. When you set S is equal to 1, you get another path out of this. This is G. And now the idea is, and this is the entire idea, that when S is between 0 and 1, so if you set anything between 0 and 1, you always begin at P, that's the condition, and you always end at Q. So that means between, so this right over here, this is when S is 0, and this right over here, this is when S is 1. And if you set S is equal to like a half, you get some kind of intermediate path that goes between them. This might be, let's say, S is equal to a half. So this, intuitively, and this is what we were saying, intuitively you are deforming one path to another path, but the deformation process always starts at P and ends at Q. That's the intuition. It's basically what's happening in this definition. Now, I want to introduce some important paths. And this is actually how we're going to get a group out of this. But for now, let's just remove this and introduce some notation. So there's some notation. Let X be a space, and P is an X. So EP, this is going to be the constant path at P. So if you're not sure what that means, a path is a function. So EP is a function from 0, 1 into X. And how is the function defined? What does it do at time T? It always gives you P no matter what. So the picture here is that if this is X, then this is the path that stays at P. So you can just say it's a point at P. Now it's technically not a point, it's a mapping into X, but when you visualize it, it looks like a point. But technically speaking, it's not a point, it's a mapping. Okay, so this is the first thing that I wanted to introduce. The second thing that I want to introduce is as follows. Say that F is a path from P to Q, and this is of course in X. Everything's happening in some topological space. F with a bar on this, F with an overbar, this is the reverse path. And this is the one that goes backwards from Q to P. Now, if you want to be a little bit more explicit about what this means, F reverse has to be a function from 0, 1 into X, because that's the definition of a path. And how is it defined? Well, the way it's defined is you take the original path, which is a function, and instead of evaluating it at t, which is what happens when you flow from 0 to 1, if you want to flow backwards, you should replace t by 1 minus t. So then, if you do f reverse evaluated at 0, that would be f evaluated at 1, which is q. And if you do f reverse evaluated at 1, that would be f of 0, and that would be p. So the picture here, of course, is if you have point P and you have point Q in some topological space X, and F goes like this, then F reverse goes backwards. Now, I cannot technically draw F reverse because it's going to coincide and be directly on top of F. So you cannot really see it. So I'm kind of drawing them in a way so you could see them differently, but they're not really supposed to be different pictures. So that's called the reversal path. The next piece of notation that I want to introduce is something called path juxtaposition. So this is the third piece of notation. Say that F is a path from P to Q, and this is of course in some topological space X, and G is a path from Q to another point, let's call it R. This is again in X. We define F juxtapose G. So this, you read this as F juxtapose G. So juxtaposition is when you're putting two things next to each other. This symbol might be confusing because if you've seen that symbol previously in mathematics, it sometimes means convolution. This is not convolution. This is not convolution. This is what we call notation overload. In math, it is very common to use the same notation to mean many different things. And we do this all the time. Maybe you'd not even realize this, but what's 1, 0 versus, what's 0, 1 versus 0, 1? So you could think of this as a point in the plane, but you can also think of this as the interval, the open interval from 0 to 1. They mean totally different things. In fact, sometimes sometimes this bracket over here, this can be like an inner product bracket. So this symbol is so popularly used throughout mathematics, but yet somehow we understand what it means without confusing ourselves. So we run out of letters, we run out of words, and eventually we run out of symbols, so it's common to just repeat the symbols again. So this is the juxtaposition symbol. Here, obviously, convolution will make absolutely no sense. Convolution is an idea in analysis, has something to do with integrating functions, taking averages, things that makes absolutely no sense here. So here, this will just mean juxtaposition. So what does this mean? This just means it's the path from P to R going along F and then G. So here's how it looks in the picture. Here's X. You have point P, you have point Q, you have point R. You have a path from P to Q, and you have another path from Q to R. We call that G. Juxtaposition is when you go directly from P to R. You first travel from P to Q, and then you use G to travel from Q to R. So how do you define it carefully? So here's how you define it. F star G, it's therefore a function from 0, 1 into X, and here's the way you define it. It's a piecewise definition. This is F of 2t. You see, the definition of a path always requires us to go from 0 to 1. That's the way we've decided to set up our definitions. So if we're always going from 0 to 1, we sort of travel twice as fast along F, so 2t. So this is for t between 0 and the half. And then this should be 2t minus 1 for t between a half and 1. Notice if t is equal to a half, this is f of 1. F of 1 is the endpoint of f, which is q. When t is equal to a half, g of 2t minus 1 will then be g of 0, 1 minus 1, g of 0. G of 0, that's the beginning point for g, which is q. So the 2 points coincide. Because these two functions agree on the overlap, so when t is a half and when t is a half, because both of these agree, this is going to be a continuous function. They glue together into a continuous function. And when t is 1, this is g of 2 minus 1. This is g of 1. G of 1, that's r. So you've constructed a path from P to R, and this is called juxtaposition. However, in general, G juxtapose F is not defined. It makes no sense. The only reason why we're allowed to do that is because by creating this piecewise function, this is still a continuous function. These two conditions agree at these two values of t, so you've constructed a continuous function. So in general, if you do it the other way around, it's not going to be defined. Sort of like matrix multiplication. If you have two matrices, A and B, A times B could be defined, but B times A might not even be defined. So this is looking like some kind of operation on paths. So this is sort of suggesting some kind of group structure arising, and this is making it seem as if it's not going to be commutative because F and G and F might be different. So that's what we want to get to. We want to get to the actual group. So let's write down some propositions that are going to show you the kind that's going to lead us into a group. Here is a proposition on path homotopy. Let's start with this one. So say F is a path, let's say this is 1, is a path from P to Q. And again, this is in some topological space X. We have that if you do F juxtapose EQ, that is path homotopic with F itself. So this symbol here means path homotopic. I know that previously we used the exact same symbol for homotopy of two maps in general, but here it means path homotopy. If you've ever used the book Moncrief's in Topology, he puts a little decoration on it by putting the letter P for path. But I'm just going to write it like this. Just going back to that theme that we overload notation in math all the time, here we are talking about paths, so it's reasonable to understand because we're using the word path that this is a path homotopy. I know we also use the exact same symbol for homeomorphism, but we get used to it. So here's the interesting thing. Doing juxtaposition with the constant path, that these are sort of almost the same. They're not exactly the same, but they're almost the same. So the reason why they're not exactly the same is if we just write out the formula for this. So let's just write out the formula for this. So you have f of t versus, and the other one is going to go like this. So juxtaposition goes as follows. It's f of 2t if t is between 0 and the half. And then it's eq of t if t is between a half and 1. And eq, I'm sorry, not t, it's 2t minus 1. But eq, this is the constant path, so this is always equal to 0. And now you can see that this function and this function, they're different functions. So doing juxtaposition like this will give you a different path. However, intuitively, it feels like they should be the same thing. So essentially what we're saying is this. F is a path, right? So it's some kind of path. It's P, we have Q, we have some kind of path. This is F. But what is F juxtapose Q? The way you do juxtaposition is you move along F twice as fast. So you just move twice as fast, and then when you reach Q, for the next half a second, you stay at Q and you never move. So if you just look at this, it appears to be almost the same path. It's just the way you're moving is sort of sped up and then slowed down, but you're still moving along the same path. So it therefore makes sense that somehow, even though these are technically different as functions, they're different. If you use this idea of path homotopy, you're sort of identifying them and you're treating them as if they're the same. You can sort of deform one to the other. That's basically what we're saying. And by the way, this makes sense because F is a path from P to Q, and EQ stays at Q. So juxtaposition makes sense. The one that is on the right has to begin where the one on the left finishes. F finishes at Q, and EQ begins and ends at Q. So this makes sense. We have this one, and we have another homotopy on the other way around. And if you do EP first, and then you juxtapose with F, that would be homotopic with F. So that's what we have. Of course, notice you cannot put EQ on the other side. That would not make sense. You see, if you were to write EQ, juxtapose F, that makes no sense. This is P, this is Q. What are you saying? F goes from P to Q. So what are you saying? You're saying you start with this one first, EQ, so you stay at Q, and then you go by F, but you're not beginning and ending at the appropriate points. So that does not make sense. So you can see it looks like this is an identity element, but not quite, because in the group, when you have the identity element, it has to be on both sides. That's not on both sides, so that does not quite make sense. So this is part one. Part two is going to go like this. Say F is a path from P to Q. Again, this is in X. We have, so if you do F juxtapose the reverse path, that would be homotopic to EP. And if you do F reverse juxtapose F, that would be homotopic with EP. So what's the picture? The picture here is you're going from P to Q, this is F, and then the reversal path goes from Q back to P. So the reversal path, it kind of goes like this. Now, intuitively, because you have this segment, you can sort of push continuously homotope that segment back to a point, and that's EP. So it makes sense why that's just a constant path. So again, this is interesting because this is sort of looking like a group. You're saying the reverse path acts like an inverse in a way, that the constant paths, they're almost like identity elements, but not quite. And the reverse path is sort of like the inverse, that if you juxtapose with it, you return back to the identities. Oh, small mistake. I did not mean to write EP over here. I meant to write, of course, EQ. So almost like the identity, but not quite, because in a group, the identity has to be left-sided and right-sided, and the inverse has to be left-sided and right-sided. But you can see it's like this is like a right-sided inverse for one identity, that's a left-sided inverse for another identity, so not exactly a group. So the next thing that I want to say is so say that F1 and F2 are paths from P to Q, and G1, G2 are paths from Q to R. If F1 is path homotopic to F2, and G1 is path homotopic to G2, then if you do F1 juxtapose G1, that's going to be path homotopic with F2 juxtapose G2. That it basically says, so we're essentially saying the idea here is that if F1 and F2 are different paths, but they are the same in the homotopy sense, and G1 and G2 are paths, they could be different from Q to R, and they're the same in the homotopy sense, then if you were to do juxtaposition, this and these will be different paths, but they will still be the same in the homotopy sense. And the next one I want to mention is 4. Say that F is a path from P to Q. G is a path from Q to R, and H is a path from R to, what's the next one? P, Q, R, S. Maybe we should not use S. S, T, I guess U. There's probably a smarter way to use notation, but I think the main point here is what matters. Then if you do F juxtapose G juxtapose H like this, and if you would do F juxtapose G juxtapose H like that, then they in general would be different functions, different paths, but the way you bracket, it would change the function, but the functions will be homotopic to each other. So that's beginning to look like the associative law that we have in the group. So we're going to not prove all of them because that would be tedious, but maybe we'll talk about some of them. So I think maybe what I'll do is I'm going to show you a proof for 1 and 2, and you can do 3. I think the easiest one is actually 3. So I'm going to do 1 and 2. You'll do 3 for homework, and 4. Well, 4 is the hardest one, so we'll put it on homework. We have good expectations that you'll figure it out. I'll give you an idea of how to do 4. How about that? I'll draw some pictures. I'll give you an idea how to do it, and then you can try doing it. So let's go through all of these. Let's look at 1. These are actually hard. So I would say these are hard, surprisingly hard. This one is easy, and this one is the hardest. But once you see how to do 1 and 2, and you see like the idea behind it, hopefully 4 is not that bad, and 3 will be actually pretty straightforward. So let's look at 1. So what are we trying to show? So we want to show, so what are we assuming? We're assuming F is a path from P to Q. We want to show, well, there's actually 2 things that we want to show, depending on whether you juxtapose with the constant path on the left or whether you juxtapose on the right. So let's do it like this. Let's show that if we juxtapose with the constant path on the right, then that would be homotopic with F. Okay, that's what we want to show. Now, so let's just calculate. This is what we said before. By the way, maybe this will make it a little bit easier. Keep in mind, f of p, that's just f of 0. And f of q, that's f of 1. Because f, after all, is a continuous function from the unit interval. So you can evaluate it at 0 and at 1. So we're going to calculate the formula for the juxtaposition. This is what we were saying earlier. This is going to be f of 2t if t is between 0 and a half. And then it's the second path, eq, 2t minus 1, if t is between 1/2 and 1. But eq, that's the constant path. So this one's just equal to q, right? That's just q. So now what do we want to do? So the goal is to construct. So what's the goal? We want to show that they're homotopic, path homotopic. So if they're homotopic, then that means there exists a path homotopy. There exists a path homotopy. So the goal is to construct a path homotopy. So let's call it H. And this is going to go from 0, 1 cross 0, 1 into our topological space X. We think of the first one as representing time along the path, and we think of the second component as representing the interpolation parameter. And this is, of course, a square, but H of, when you set S is equal to 0, that should give you, so it's up to you which one you want to be the first one and the second one. I'm going to make this be the first one. This is the first one, and we're going to homotope it into the second one. So this is going to be our first path. So this is f of t. When you set s is equal to 1, that would be the other one. That would be f juxtapose eq at t. And the additional requirements is, this is the additional requirements in a path homotopy, that if you do h, if you set t is equal to 0, then for any s, that should always be p. And when you set t is equal to 1, then for any s, that will always be q. Because these are the interpolated paths that always move from p to q. That's the idea. So that's what we want to do. And what is this? We're therefore defining it on a square. So let's draw a square. This is the unit square. So let's define it on the unit square. That's the unit square. So the horizontal coordinate is t, and the vertical coordinate is s. So notice when s is equal to 0, this lower edge is supposed to be f of t. So this lower edge is supposed to be f of t. That's the function you're supposed to get on the lower edge. When you set s is equal to 1, you're getting this function. And this function is a piecewise function. It's supposed to be f of 2t from 0 to a half, and from 1/2 to 1, it gives you the other one. So let's cut this in half, like this. And on this piece, you're supposed to get f of 2t. So this portion is supposed to be f of 2t. And the second half of the interval, from 1/2 to 1, you have to get the other one. Maybe we'll write it like this. You're supposed to get q. This is just q. And the way we'll do it is, so this is the picture. This picture is the big, it's not so easy to do, but what we'll do is we'll draw a line that connects them together. And the way this function will be defined, it will be defined depending on which side you fall into. So h of t comma s, this will be a piecewise defined function, and there will be two conditions. The basic idea is that if s is some number between 0 and 1, notice there's two regions. You're either in the left region or in the right region. So it makes sense to find the equation of this line. So let's say what the equation of this line is. So the equation of this line, this is sort of like x and y. So you would say y is equal to x, in this case t, times the slope. The slope, it's from 0, it goes up a half and it goes up to 1, so the slope is 2. Or if you solve it the other way around, t is a half s. We're going to solve it for t because the idea is if we keep s fixed, we want to find the cutoff interval exactly at what moment in time that happens. So the conditions will go as follows. We would say if, let me do it like this. So if t is between 0 and a half s, then we should be on this side, right? We're going to put something here on this side, and then, so I realized something that's a little bit annoying as I'm doing this. I realized that I want to show this, right? Now, the reason why this is a little bit annoying, you have to change the picture. Basically, if you look at the picture, f of t is on the right side of this divider, and f of 2t is on the left side of the divider. That's a little bit annoying. You have to draw the picture a little bit differently. So technically, I should have drew the line not like this, but really I should have drawn the line going like this. So it's easy, instead of changing the pictures all the way around, it's going to be easier to change what we want to show. So instead of showing this, so you can show that. I'm going to do, to make the picture work out correctly, I'm just going to change this up a little bit. We're rather going to show it the other way around. We're going to show that if we do EP juxtaposed F, it's going to be homotopic with G, because I do not want to change the picture now. So then this would be EP juxtapose F. And then this one would be F of T. I'm sorry, not F of T. That would just be P. And then the other one would be F of 2T minus 1. And then the modification we need to do here is this one should be E P juxtapose F. And everything will stay the same. And now I just have to make a small little modification that the first one, the way we're doing it, the first one has to be P. And the second one has to be F of 2T minus 1. So sorry about that small little minor mistake. But I actually think it's good when you're doing these live lectures and you make these small mistakes along the way, because then you're showing to the audience the thinking process rather than just having a PowerPoint that immediately shows you the answer. So you kind of get to see it. You kind of see the development of the thought process behind this. So, so look at this. When you're on the left side of the divider, it should be equal to P. So let's just set that equal to p. So that would just be p. And if you are on the right side of the divider, so t between a half s and 1, this is the part that's a little bit tricky. It's not as easy as it seems. At first you might be something like, oh, let's set it equal to t. So here's the problem. You cannot just naively set it equal to f of t. Unfortunately, that's not going to work. The reason why this is not going to work is because notice the lower edge is f of t, and the upper edge is 2t minus 1. So somehow there is a change in coefficient. The coefficient in front of the t variable has to gradually change from 1 to 2. So within here, you're supposed to reflect that somehow. The other thing that's supposed to happen is that these are the overlapping conditions. This is supposed to be a continuous mapping. If this is a continuous mapping, then on these overlapping conditions, this one and this one need to be the same. Now, what is f of p? F of p is another way of saying, I think this will make it easier, that's another way of saying f of 0, right? P is the initial point, so that's just f of 0. So when t is equal to a half s, so when you're right on the line, when t is equal to a half s, it's supposed to give you f of 0. So it's reasonable to try doing this. Let's say we do f of t minus a half s, like this. So then you can see that by setting t is equal to a half s, this will become 0, and that's just f of 0. And this is f of 0. So then they agree, and that's a continuous function. The problem is the slope, well, not the slope, I should say the coefficient in front of t, it's supposed to go from 1 to 2. So you have to sort of modify this by dividing this out by something. So you're going to divide this out by, I think, so let me just try doing this, and hopefully this will work out. I think this should just be 1 minus a half s, like this. Because when, yes, so if t is equal to a half s, the numerator is 0. So that's just f of 0. So on the overlaps, they agree. When s is equal to 0, that's the lower edge. When s is equal to 0, you get f of t. Now, notice what happens if s is equal to 1. If s is equal to 1, this is f. So what is this going to be? This is going to be f of t minus a half divided by 1 minus a half. And if you just simplify this, this is 2t minus 1. That's exactly what we wanted. It's supposed to be f of 0 from t to a half, and from the other piece, it's supposed to be 2t minus 1, f of 2t minus 1, which is exactly what we want. So this is the way you have to do it. So you can see it's not that easy. You have to somehow modify this a little bit. But the point is, all of the conditions are satisfied. This is a continuous map. This is a continuous mapping because on the overlap conditions, these conditions agree. When s is equal to 0, you get the lower edge function. When s is, you see, when s is 0, from t from 0 to 0, that's not doing anything. And so you're going from 0 to 1, so you're getting the lower edge. When s is equal to 1, the other extreme, you're going from 0 to a half. That's the first interval. From s is 1. So from 0 to a half, you get f of 0, which is p. And then from 1/2 to 1, you get the required function f of 2t minus 1. And then this continuously moves from 0 to 1. And then finally, these conditions are satisfied. If you set t is equal to 0, t is equal to 0, right? T is equal to 0. That's f of 0. That's p. If you set t is equal to 1, you're in the second condition. So you set t is equal to 1, that's 1 minus a half s divided by 1 minus a half, which is f of 1. F of 1 is the right endpoint, q. So everything works out in the end. But it's not that, as you can see, not that easy. Now, based on this theme, let's do the other one. So let's show. So now let us show that if we do, so this is the one that we want to do with the reversal path, that if we go, let's say, f juxtapose f reverse, that should be homotopic with EP. So here f is a path from P to Q. So let's work this out. So EP of t, this is just a constant path t. That's not very interesting. But f juxtapose f reverse at t, this is going to be given by piecewise conditions. So the first one is going to be twice as fast. So this is f of 2t. And the second one is the reversal path 2t minus 1. This is for t between 0 and a half. And this is between 1/2, and 1. But then you recall what the reversal path is. So the reversal path, it's the original path. So it's the original path. This is without the reverse. And it's 1 minus whatever the original was. So that's 2t minus 1. This is if t is between 1/2 and 0. And this is if t is between 1/2 and 1. And now you get to simplify this a little bit. So this would be 2 minus 2t. So that is what we get. Double minus, so that's 2 minus 2t. So to show that f juxtapose f reverse is homotopic with EP, we need to construct a path homotopy. Let's call it H, from 0, 1, cross 0, 1, into our topological space X. Let's call this one S. Let's call this one T. And the properties, the same properties have to be satisfied, that H of T comma 0 should give you the, let's say, the constant path, which is always equal to P. And H of T comma 1, when you set S is equal to 1, this is the one that gives you the juxtaposition at T. H of 0 comma S should always be P, and H of 1 comma S should always be Q for every S. So here, what we will do is we're going to draw a square just like before. This is going to be T, this is going to be S. So on the lower edge, when S is equal to 0, we're going to have the constant path equal to P. On the upper edge, we have to have this juxtaposition. But this juxtaposition has two piecewise conditions built into it, from 0 to 1/2 and from 1/2 to 1. So this one gets cut down the middle like this. So the first piece should be f of 2t, and the second piece should be f of 2 minus 2t. And this is sort of like the divider down the middle. And this one's going to be a little bit harder. Here what you would do is you would draw your lines in this kind of triangle. And then if you have an intermediate value of s between 0 and 1, you will have three conditions. So h of t comma s would be a piecewise function with three conditions. So you would say if t is between 0 up to, so you have to go up to the equation of this first line. Well, this is just what we did in the previous proof. The equation of that line is t is equal to 1/2 s. Then you would say if t is between 1/2 s, you have to figure out the equation of the other line, and this is if t goes up to 1. So a little bit of playing around with this should convince you that this line is 1 minus 1/2 s. That should not be too difficult. It has negative slope because it goes the other way, so it makes sense it's negative 1/2 s. So I'm sure you can figure it out. If you cannot figure it out, then unfortunately, topology, the course is probably a little bit too advanced for you. This is like the boring part of the calculation. But now that you found the equation of the three of these two divider lines, you'll have three different conditions. On the left one, you would have you're going to use f of 2t on the left one. So on this one, you're going to write f 2t. On the right one, you're going to write f of 2 minus 2t. And it's the one that's in the middle, which is the tricky one. And basically what you need to satisfy is you need to satisfy the requirement that on the overlaps, so this is the overlaps, that on the overlaps, that they're compatible. So if you set t is equal to 1/2, what you get over here should be consistent with what you get over here. So notice if you set t is equal to 1/2, then you would get f of t 1/2 s. This would be f of 2 times 1/2 s. So that would be f of s. So the one in the middle should be f of s. And to check that this actually works, we have to check the other compatibility condition. We have to check if on this overlap, with that overlap, the two functions agree. So if you set t is equal to 1 minus 1/2 s, and you put it in here, so let's see what happens. So you would have 2 minus 2, and t is 1 minus 1/2 s. So this would be 2 minus 2 plus s. So that's just s. So again, they're compatible. So this is a continuous function. Then you can check all of the requirements. If you set s is equal to 0, so if s is equal to 0, then from 0, well, if s, yeah, what happens if s is 0? So let's do that. S is 0. What do we get? So then we get f of 2t for t between 0 and 0. We get f of 0 for t between 0 and 1. And then we get f of 2 minus 2t for t between 1 and 1. So if t is between 0 and 0, that's just f of 0. That's f of 0. And this is t is equal to 1. So that's f of, so all of these are f of 0. So what are you getting? You're getting the constant path, f of 0. That's the point at which you start. So that's good, right? If you set s is equal to 1, then how do the conditions change? Then this goes from 0 to a half. This one will go from a half to a half. Half. And that should be, s is equal to 1. So from 1/2 to 1/2, this is f of s, a half. I'm sorry, s is 1, so it's just f of 1. And then from a half to 1, there should be 2 minus 2t. And that's exactly what we want. From 0 to a half, it's f of 2t. When t is a half, f of 1, that's just the ending point, that's q. That's where they begin and end, and it's the other one. So that works out. And then finally, the last condition you need to check is you need to check what happens when s is 0. I'm sorry, when t is 0. So when t is 0, you get f of 0, but f of 0 is p. That's the beginning point. And if t is equal to 1, you get f of 1. That's the right endpoint, so you get f of 1, which is q. So all of the conditions, as you can see, are satisfied here. And now this brings up the most difficult one. So the associative, so I'm not going to prove to you the associative property. Instead, what I'll do is I'll give you an idea of how you would set this up, and then you try to do it. So this is the idea for the associative So we want to show f juxtapose g juxtapose h should be homotopic with f juxtapose g juxtapose h. These are going to be different functions. So maybe what we'll do is let me call this L for left, and let me call this rho for right. So L juxtapose h at t would be the function. So this is homotopy, of course. But L juxtapose h at t would be the function. It's L of 2t if t is between 0 and a half. And there would be h of 2t minus 1 if t is between 1/2 and 1. But now you have to figure out what is L. So maybe instead of using the letter t, let's use a different letter. Let's call it a. So L at a is f juxtapose g at a. So that would be equal to f of 2a if a is between 0 and a half. And then this one will be g of 2a minus 1 if a is between 1/2 and 1. So this means that if you put in a 2t, if a is replaced by 2t, what would you have? So you would have that L of 2t would be equal to f of 2a, but a is 2t. So that would be f of 4t if 0 is between 2t between a half. And then the other one would be g, so a gets replaced by 2t. So that would be 4t minus a if 2t is between a half less than 1. So now if you rewrite these inequalities, you're saying for t between 0 and a quarter, and here you're saying for t between 1/2, and 1/4. So to basically summarize the whole thing, this is what we have. F juxtapose G juxtapose H. So this is a function. This is a function. It's a path, so it depends on time. This is L juxtapose H at t. So all what we've done was L represented this. But now, when you open this up, you have L of 2t. So it's this one. So it will have 3 pieces here. It would be F of 4t if t is between 0 and 1/4. Then it would be G of 4t minus 1 if t is between 1/4 and 1/2. And then finally, it would be H of 2t minus 1 if t is between 1/2 and 1. So it's quite complicated, but basically the interval from 0 to 1 is cut down the middle, and then between 0 and 1/2, it's cut down the middle again. So you're basically doing it in succession. You're first activating F, then you're activating G, and then you're activating H. So this is the way this one goes. The other one, if you do it the other way around, if you have F juxtapose G juxtapose H, and you try to work out the formula, I'm not going to tell you what the formula would be, because that's for you to figure out. But the way you'll have 3 conditions, and it's going to go like this. It would be t between 0 and 1/2. Then it will be between 1/2 and 3/4. And then the other one will be between 3/4 and 1. And you just have to figure out what the functions are. So here the picture would be that on the interval from 0 to 1/2, you put 1/2 in the middle, and now you put the midpoint between 1/2 and 1. So that would be 3/4. And now the situation is a little bit different. You first activate F over that interval, then you activate G over that interval, and then you activate F over the remaining interval. So this is the composition, I'm sorry, not the composition, the juxtaposition that you get when you do it with the brackets the other way around. And you want to show that these are in general going to be different functions. But even though they're different functions, they're different paths, there's a path homotopy between them. So when you construct the path homotopy, the way the picture is going to go is you're going to have your square, and on the lower edge of the square, you will activate it in this way. You will have 1/2, and you would have 1/4. Maybe I'll just put the divider like this, and then one here, then this is 1/2, and that's 1/4. And then you're going to draw a line going like that. You're going to draw another line going like this, so 2 parallel lines. And this is basically, the lower one is going to be F of something, then it's going to be G of something, and this is going to be H of something. And on the top, you have something very similar, F of something, G of something, H of something, like that. And we actually written out what those somethings are right over here. And then you do something similar for the other one. And then the way you get the homotopy map, it's going to be the same idea, that you'll have 3 conditions. You'll have something if t is between 0 up to the first line, line 1, and then t between line 1 and line 2, you have another condition. And then if between line 2 and 1, you have another condition. And you will have to make sure that the conditions are set up in some kind of compatible way. It's pretty tricky, because you will notice that the slopes, well, maybe I should not say the slope, but the coefficients, they change. On this lower one, it's f of 4t. So I can actually tell you what these are. So this one, this is f of 4t, and this one is going to be f of 2t. So the coefficients, they change. So this is a little bit similar to the first one that we did, that you somehow have to put the s inside the f itself, so that the coefficient appropriately changes when you reach the end. So it's kind of tricky to figure it out, but it's basically trial and error. You just try something, it does not work, then you slightly modify it, and you keep on doing it until it finally works out nicely in the very end. So now, with all of this information, we can actually get to how you get a group out of all of this. Instead of considering all paths, so let's do this. Let's fix some point in our topological space X. And we're going to specialize to closed paths that begin and end at P. For any loop, So by a loop, we just mean a closed path that begins and ends at P. For any loop F, so it's a mapping, right? F is a mapping from 0, 1 into X. F of 0 and F of 1, they're equal, and they're both equal to P. So for any loop, we denote F with square brackets. This is called the homotopy class of F. And this is the collection of all closed paths. So this is going to be all closed paths with the property that, so it's also a closed path, and G is homotopic, path homotopic, of course, with F. So to put it very simply, this is the set of all paths, closed paths, and this is at P, of course, which are homotopic with F. So that's what that is. This is what we call the homotopy class. This is quite common notation in mathematics. Whenever you have a particular type of object and you want to treat other objects as similar to that object, when you put square brackets around that object, you then indicate the collection of all objects that are equivalent to it. So here equivalence is homotopy, path homotopy equivalence. This is similar to when, for instance, you talk about integers mod a certain number. So integers mod 5. So 3 mod 5 and 8 mod 5, they're different. 3 and 8 are different, but mod 5, you treat them as the same. So then the class of 3, this is the mod class of 3, will also contain the number 5 in there and many other numbers. So this is the same idea. So we specialize to closed paths. Okay, and what we do next is then we define the fundamental group of X at P. This is then going to be the collection. This is the collection of all homotopy classes. So you would write that the homotopy class of F is an element of the fundamental group. That's just one of the elements. The other elements would be the other homotopy classes. So here's how we get a group. So let's say we have F, let's say we have F1 and we have F2. So these are homotopy classes. We define multiplication. So we have to define multiplication. So we say that multiplication is defined by juxtaposition. We take F1 and we juxtapose it with F2. That's the way multiplication is defined. And you can check this is what we call well-defined. Well-defined, I'm sure you heard this term many times before. It just means that the choices do not matter what representative you pick. So you're using F1. So this is an equivalence class. In general, it will contain an infinite number of loops that are all homotopic to each other. And you're just picking one of them, which you're calling F1. So you multiply two equivalent, you multiply two homotopy classes, you pick a representative for the entire class, you pick another representative for the entire class, and then you perform multiplication by using those two representatives. You juxtapose them together, you get something, and whatever you get, you consider the homotopy class of that entire thing. And it does not matter what representatives you pick. This is one of the statements in the proposition that if you replace F1 by let's say G1, and F1 is homotopic with G1, and you replace F2 by G2, and F2 is homotopic with G2, then this juxtaposition will be homotopic with the other juxtaposition. So they will give you the same answer regardless of what you do. And then the other thing is, we also have that if you do F and you multiply it by the homotopy class of the constant path, then this would be F juxtapose with EP. Now here's the big idea. F juxtaposed with EP in general is not equal. See, F in general is not equal to this. They're different functions, but they are homotopic to each other. That's sort of the whole point of this. That yet you might be getting something different, but on a homotopy level, these two homotopy classes are actually the same. So the homotopy class of the constant path acts like an identity on the right, and it also acts as an identity on the left. The reason for that is because I know that previously we talked about EQ and EP, but these are closed paths. EP and Q are the same. That's the whole point of using closed loops. That problem of whether you're on the right and left, it kind of goes away. That's the advantage here. So this would be EP juxtapose F, but as we said, that's homotopic with F. Finally, we also have inverse. If you do F juxtapose the reversal path, that would be F juxtapose the reversal path, and that's in the same homotopy class as the constant. And it's true the other way around. So F inverse exists. So one of the requirements for a group is to have an inverse, and the inverse, the way you find it, so we have the inverse of the entire class. It's you take the reversal path, and it's the homotopy class of the reversal path. So that is very nice. And of course, we have the associative law, right? And we have the associative law that if we have F times G bracket times H, well, that would be F juxtapose G multiplied by H. So then that's equal to F juxtapose G juxtapose H. But that's the same thing as, that's exactly what we were saying before, doing it like this. So in the end, it gives us F bracket G bracket H. So the associative law also is satisfied. So we have a group. So we will not get a group if it was not closed paths. It's important that it has to be closed paths. So this is the fundamental group. And this is very useful in topology. You can use it to solve, it can help you solve various topological problems by working with the fundamental group. Now, I should make a comment about what happens if you have a different base point that is being used. So basically the question is this. So here's the question. So what's the difference between taking the fundamental group at this point and taking the fundamental group at a different point? Now, obviously, they're going to be different groups because this is going to be the collection of all homotopy paths that begin and end at P, and this is going to be the collection of all homotopy classes of paths that begin and end at Q. So it's a different collection of things. But when we're dealing with groups, we often do not care what a group is as a set. We care whether or not two groups are isomorphic to each other. That's like one can say is a more, like a deeper thing to ask. So the proposition, so this is the proposition. So here's the way the proposition goes, that suppose X is a path connected space, and P and Q are points in X. Then the fundamental group of X at P and the fundamental group of X at Q are isomorphic groups. So as groups, they're not really that different, are isomorphic groups. So here's how we prove it. It's actually a fairly nice proof. And then after this proof is finished, we can look at some examples, some important examples to know. So let's discuss the proof of this. Let's draw a picture. So let's say this is X, this is P, this is Q. So here's the way the proof is going to go. Since X is path connected, let's choose any path. Now you can have many paths, but choose any path F from P to Q. Right, so it could be anything. So you just choose any path from P to Q. That's going to be F. Now here's the idea. So observe that so I want to use a letter that goes in a circle to sort of indicate it's a loop. So observe that if, let's say theta, I like to use theta because it goes in a circle. So let's say theta, so let's draw theta right over here. That's theta. Observe that if theta is a closed path at P, then, so here's how you can get a closed path at Q. So you're first going to go from Q to P by using the reverse. So you're going to do F, the reverse, then you will juxtapose with theta, and then you will flow back by F again. Then this is a closed path at Q. Okay, because notice what happens. Theta travels from P to itself. So if you first start with the reversal path, you're going from Q to P, then you follow through by theta, and then you travel back by F. So you're back at Q. So this calculation will begin and end at Q. So this is a closed path at Q. Okay, so define the following map. So I'm going to call this map mu for map. So this is going to be a map from the fundamental group of X at P to the fundamental group of X at Q. And so what are we trying to show? We're trying to show that these two groups are isomorphic. So how do you show that two groups are isomorphic? So let's just go back to group theory. Let's say you have a group G1 and G2, and you want to show that they're isomorphic. So you have to define a mapping, let's call it mu, from G1 to G2. This should be a bijection and a group homomorphism. So that's the way you show that two groups are isomorphic to each other. So that's exactly what we're trying to do here. We're trying to show these two groups are isomorphic. So we're going to define a bijection that's also a group homomorphism. So we're going to define the following map, XP. So from this one to that one. So how is it going to be defined? So here's how we do it. So as follows. So we're going to choose a homotopy class in this one. So this means it's a homotopy class of closed loops that begin and end at P. And we're going to say that mu of that entire thing is going to be equal to, by definition, that's the way the mapping is defined. We're going to do it like this. It's going to be F, reverse, juxtapose theta, juxtapose F. And it's the homotopy class of this one. That's going back to what we said in the beginning. We made the observation that if theta is a closed path that begins and ends at P, this calculation will give you a closed path that begins and ends at Q. So this is now something, it's a closed path at Q, at the other base point. Now, I want to make a very small, subtle point that can lead to some confusion. So you want to be careful. Be careful. You cannot say that that's the same thing as this. So this is F reverse. So then you would say this is F inverse theta F. You cannot do that. The reason why you cannot do that is because this does not make sense, and this does not make sense. You are in the fundamental group at Q is, by definition, it's the collection of homotopy classes of closed loops that begin and end at Q. So this one makes sense. The one in the middle makes sense because theta is a closed loop. Well, I'm sorry, theta is a closed loop in this one, right? It's in this one. That's a closed loop in on the group on the left. So that makes sense. But these do not make sense because F is not it's a path from P to Q. It's not a closed loop. So when you put the brackets around it, that's the homotopy classes of closed loops. So we should not be writing this. There's a reason why we leave it like this. This does make sense. This is the homotopic. This calculation is a closed loop at Q. So that actually makes sense. Okay, so, but this is the way the map is defined. And there's a small technicality, there's a boring technicality. This is the boring detail to show mu is well defined. Well defined. Because we are, again, choosing a representative. What if you had, instead of theta, you had theta prime? And theta prime were homotopic. Would this be homotopic? It would be. It's just a small detail that one has to address. But you have this mapping. And the claim, and we claim that mu is a bijection and a group homomorphism. So since this lecture is, as you can see, fairly long, I'm going to do one of these. Let me prove to you that it's a group homomorphism, and it will be up to you to prove that this is a bijection. None of these are actually that difficult. The difficult part is actually recalling the definitions, but the proof itself is fairly straightforward. There's nothing clever that's being done. So let's just check that it's a group homomorphism. So to show that mu is a group homomorphism, we need to show that if you do mu of theta 1 multiplied by theta 2, that's the same thing as mu of theta 1 mu of theta 2. So let's work this out. We have that mu of theta 1 times theta 2 is equal to mu of, now the way you multiply equivalence classes or homotopy classes is by juxtaposition. So to repeat this point again, because this is an important point, the reason why we can remove the dot and put them together is because these are closed loops. The reason why we cannot break them apart by using 3 different dot operations is because f is not a closed loop. That would just would make no sense. We have to keep it like this. So by definition, multiplication of homotopy classes of loops is juxtaposition. And mu of this, so using the definition above, that is equal to, it's the homotopy class. And I should say that, I should have probably said this a little bit earlier, but this bracket represents the homotopy class of x at P. This bracket is representing the homotopy classes of x at Q. So we're again overloading notation. We're kind of using the same bracket, but they technically mean different things. So, and the way this is defined is, this is going to be f juxtaposed, so this is going to be f juxtapose theta 1 juxtapose theta 2 juxtapose f. And if you do it the other way around, if you do mu of theta 1, so now we have to check the right side. We have to check this and this. This would be, so this one would be f theta juxtapose f, and this one would be f juxtapose, this is theta 1, theta 2 juxtapose f. But now, because this is a closed loop and that is a closed loop, we can now put them together into this larger bracket, and we would have, that's quite a lot of brackets. So we have this one, and then we have this one. And now the associative law basically comes to the rescue. And even though we have a lot of brackets, basically what the associative law says is that you can basically get rid of the brackets. So if you, I mean, it looks complicated, but if you get rid of the brackets, this should look easier. It's this theta 1 f reverse theta 2 and then f. And now the whole point is, notice the f and f reverse are next to each other. So this is the identity path at P, the constant path at P. And juxtaposition with the constant path does not do anything. So you end up with this, which is basically what you have there. Say basically because I'm being a little bit sloppy with the bracket, but that's the associative law that says that the bracketing does not make any difference. Because we are working with homotopy classes. That's the whole point. We're working with homotopy classes. That even though the functions, the way you bracket it does change the functions, juxtaposition does depend on how you bracket, the homotopy class does not. So that's why we can get away with doing all of that. And so it's a group homomorphism, as you can see. It works out nicely. And then for you, you can just check that it's a bijection. So now I want to get to some examples of certain spaces that you should be familiar with and what their fundamental groups are equal to. So here are some important examples to know of fundamental groups. So some examples. So let's start with perhaps the easiest one, and that's what happens when you have a convex region. So say that C is some region in Rn is a convex region. And you're going to pick any point in your convex region. So then the fundamental group of this convex region at this point is, so we just say it's the zero group. It's just a trivial group. Now, if you're not sure what that means, is it's a group that it's the group of just one element. So the elements in the fundamental group are homotopy classes, and you always have the constant class, the homotopy class of the constant class. So maybe like more specifically, every closed loop in C at P can be homotoped to a point. That's what we're saying. So if you have a convex region, so here's like a convex region, and here's some point P, I think it makes sense that you can, because you have all that, since it's a convex region, the stuff inside that loop is part of the space, and so the idea is you can keep on moving it down until you reach a point. So let's actually prove something that's a bit more generally. So to prove this, we will rather show a more general fact, namely, if f and g are two paths in C from P to Q, so it does not have to be closed paths, then f can be homotoped to G. And then in particular, if it's true for all paths, it is certainly true for closed paths, because that's like a specialized case. And the proof of this is actually very simple. You're going to use the fact that it's convex. So here's the proof. Let f and g be two paths in C. Construct the following homotopy. Let's call it H. So just like before, this is go from 0, 1 cross 0, 1 into C, into your convex region. This one's going to represent time. Let's say this one represents time, this one represents interpolation, and we're going to do it as follows. So H of t comma s is, here's the way we do it, f of t. So maybe I should draw a picture. So I think a picture would be very helpful here. So here is a convex region C. You have 2 points, P and Q. And you have a path, F, and you have another path, G. The idea is, because, so now if you pick something over here, let's use a different color. If you pick something over here, F of t, and you pick something over here, G of t, this one should have been G, then because it's convex, the line that connects them is part of your space. You see, it's important that you always end up in your space. It's a homotopy in your space C. And the way you get the line in between them is, this is the way we do it. It's 1 minus s times that plus s times g of t. So as s ranges from 0 to 1, you're moving from f of t to g of t. So you get the line. This is, of course, a vector because this is an Rn. That's a vector in Rn. These are scalars. But this makes sense. This is a continuous mapping because you're just combining continuous functions together. Notice if s is 0, you get the first path f. If s is 1, you get the second path g. And also, if you set, let's say you set t is equal to 0, this is 1 minus, so let me just show you what happens. So if you set t is equal to 0, 0 comma s, that would be 1 minus s. So f of 0, that's the beginning point, plus s g of 0, that's the beginning point p. So that's p. So in the end, that's just going to be p, right? So that gives you the point. So the point is, this is a path homotopy. It's giving you this interpolated path between p and q. They always begin and end at q. So this is a nice fact to know, that if you have a convex region, then its fundamental group is going to be trivial, which is just another way of saying that all closed loops can be shrunk down to a point. Now here you have to be a little bit careful. So be careful. Well, actually, let me make a definition first. We say that a space X is simply connected if and only if X is path connected, so we know what that means. And the fundamental group of X at any point that does not matter, they're all isomorphic, is trivial. So convex regions are simply connected, but not conversely. So I'll give you a very simple example. Let's say you look at something like this. This is your X. You can see from the picture that this is not convex, but yet at the same time, if you have any closed loop, it seems to always include the stuff inside of it. So you have room to shrink that loop down to a point. It's like you basically have no holes in your space. That's the idea. That's what it means to be simply connected. Intuitively, it means there's no holes. So convex regions are simply connected, but it's not true the other way around. Now, let me show you some other examples. So an example you probably want to keep in mind is S2. This is the two-dimensional sphere. S2 is simply connected. It's not convex. So if you look at the picture, if you have, I mean, clearly it's not convex, because if you pick 2 points on the sphere and you connect them, the line that passes through the center, that's not part of the two-dimensional sphere. So, however, if you have a closed loop on the surface of the sphere, you can keep on shrinking it down to a point. So just take a ball, put a rubber band around the ball, and then you can keep on moving the rubber band until it comes down to a point. So that's really what we're saying. So that would be an example of that. Another, yeah, so far all of the examples were trivial groups. That's the two-dimensional sphere. And also Sn, the n-dimensional sphere, is simply connected for n bigger than or equal to 2. The one-dimensional sphere, that one is more interesting. So we'll talk about that. So far, every single example we gave, the fundamental group was trivial. So now we give our first non-trivial example of the fundamental group. This is perhaps the most important example. The fundamental group of the circle. So pi 1. So how do we typically think of the one-dimensional sphere? So the most convenient way we think of the one-dimensional sphere is we think of it as complex numbers whose absolute value is equal to 1. Okay, so a plus ib, that's z, and the absolute value of z is a squared plus b squared square root. So that's the way we typically think of S1. So the fundamental group of the circle, the unit circle, it does not have to be a unit circle because this is topology. The size does not matter. The fundamental group of the one-dimensional sphere, the circle, and you pick some point. Let's say the most convenient point to pick is 1. We usually like to pick 0, but 0 is not part of our space because its absolute value is not 1. So 1, right? This is just 1 plus 0i. So then the fundamental group of this is isomorphic to a well-known group, right? This is isomorphic to a well-known group, and that group is the group of integers. Now, maybe this is not quite clear. So we're saying it's isomorphic to Z, but maybe that's not the most satisfying way to put it, because you're probably thinking, well, what do the homotopy classes look like? So here's how they look like. We're going to draw a circle. This is the point 1, okay? And we're going to let, let f of t, so f is going to be a map from 0, 1 into the circle. We're going to use Euler's formula here. So it's e to the 2 pi I t. So this is a complex number, and as t ranges from 0 to 1, the absolute value of this number is 1. So you go counterclockwise around the circle when you use this. This is, of course, by Euler's formula, this is cosine 2 pi t plus I sine 2 pi t. So this is what you get the parametrization of that loop that goes around one time. Kind of funny, we have a pi over here and we have a pi over here. Another example of overloading notation, but we're not going to make a big deal out of it. We understand these are 2 different pi's. In fact, I like it when I have like 3, 4, 5, 6 different pi's in the same equation, and then it's an exercise to understand which one is which. It's a good way to pay attention. But anyway, so basically, f is the loop that winds around one time counterclockwise. Now, if you do f juxtapose f twice, this is the loop that winds around 2 times. And you can do a simple calculation here. Let's actually do a calculation. If you do x juxtapose with f itself, this is going to be equal to f of 2t if t is between 0 and the half, and then it's f of 2t minus 1 if t is between 1/2 and 1. This one, of course, will become e to the 2 pi I 2t, and this one will become e to the 2 pi I 2t minus 1. And this is e to the 2 pi I times 2t, and then e to the 2 pi I minus. But by Euler's formula, this is just 1. So you're actually getting the same thing. So you're basically getting that this is the function e to the 2 pi I. Instead of t, you have 2t. But keep in mind, t ranges from 0 to 1. And so really what you're doing is you're winding around. You're basically traveling twice. The loop travels twice around the circle. Okay? And then you can do it 3 times and 4 times and so on. So basically, this is what's going to happen. So if we remove all of this, so this is how you're getting the integers. So the integers come up based on how many times you go around the circle. Now, I know at the moment, we did not prove this. In my other topology course, we actually proved this. But if you've never seen the proof and you're not familiar with this, you do not have to worry about it because we'll prove it later on in the semester as the course goes on. So I just want to get this out of the way so that we at least know what the fundamental group is. So basically, this is the way it's going to go. You're going to have what we just said, f, the homotopy class of f. Now notice we're writing over here the homotopy class of f because in general, a closed loop does not have to nicely at uniform constant speed go one time around the circle. A loop can be a lot more complicated. It can do this. It can go forward, then it can suddenly backtrack, go forward, backtrack, speed up by a lot, backtrack, and then kind of go forward past it and then return back here again. So it does not really matter so much that it does that, you just have to count how many times it actually transverses around the circle, complete revolutions around the circle. This is something we're going to prove. At the moment, it's not exactly obvious how you prove that, but we'll prove. I mean, intuitively, I think it makes sense. So this is the one that goes around one time. Then you would have f juxtaposed f. This would be f squared. That's doing it twice. F cubed. And then you have the identity, which is f to the 0. This is just another way of saying E1. That's the homotopy class of E1. That's the path that stays at E1. So let me give you an example of a path that would be homotopic to it. So imagine your path did this. You went forward, and then you returned back again, like that. You did not actually transverse all the way around. Well, it's clear that because you're not going all the way around, you can just take that endpoint, and you can like carefully, slowly homotope it back to 1, and you can homotope it back to the constant loop. So, so this is the one that goes around 0 times. And then you would have f inverse. So f inverse, this is the one that goes in the reverse direction. So this is the one that goes clockwise. And this would be f to the -2 and so forth. So that's how you end up getting the integers. So it's isomorphic to the integers. But of course, when you write it out like this, it's nice to see the actual description of what the homotopy classes are. So as I said, at the moment, we just accept the result, and then we're going to prove it. We're going to prove this afterwards. So for the next example that I wanted to mention, this one is rather interesting, and it's x. Let's say x is the torus. So a torus, I'm sure you all know this. It's a space that looks like this. Let me call this the concrete torus. Usually in topology, we describe a torus very differently. There's many different ways of describing a torus, because in topology, what we care about if the spaces are homeomorphic or not. There are simpler ways of describing a torus, because the concrete way of describing the torus, the way you've probably seen it your first time, is you actually have to write out the equations for the torus, which are not exactly super convenient. It's like those sine cosine equations. But it does not really matter because they're all homeomorphic. So the concrete torus, the way it goes is that you take this kind of circle, and then you revolve it around one of the axes. As you revolve it, you get a piece, some kind of shape that goes like this. So like a donut type of a shape that goes like this. So usually with the way we draw it is we draw it like that. So we kind of draw a piece, we draw that hole, and that is your torus. The way we prefer to work with a torus in topology is by using something called an abstract torus, which does not look like anything. It's just a collection of sets and elements, but it's much more convenient to actually prove things with the abstract torus. We'll see other ways of describing the torus if you've not seen it later on. But for now, just think of the very concrete torus where you have two radii. You have the small radius that goes around this one, and then you have the revolution radius, the larger radius that goes around the other one. So you have something that looks like this. So then this is some region sitting inside Euclidean space. And I should say that this is hollow inside. This is a two-dimensional torus. It's not filled in inside. It's just a surface. So that's the torus. And the fundamental group, so the fundamental group of the torus at a point, it does not matter. So you have some point. It does not matter where you pick the point. Let's say you pick it right here, P, at some point P. The torus is, of course, simply connected. So they're all going to be isomorphic to each other, regardless of where you pick the base point. So this group is isomorphic to the group. It's two copies of the integers. And let's actually describe what the homotopy classes are. Because when you write it like this, it's not really saying too much about the topology. I think it's nicer if you actually write out what the homotopy classes are. So here's how it goes. So one of the homotopy classes, you would go around this one. You choose an orientation. Let's call this one alpha. And then the other one, this is the closed loop that begins at P and ends at Q. I'm sorry, ends at P, and it goes around this one. This is the one that you pick an orientation. You're going to call that one beta, let's say. And then there's an interesting relationship. Now, I think it's intuitively clear that the homotopy, that alpha is not homotopic to beta. Because if you put a rubber band around this piece, no matter how you try to slide the rubber band, it will always go around that hole. You cannot make it go sideways to go around that one. It is one of those things that is intuitively clear, but proving it is, of course, harder if you want to try to prove it rigorously. But you not have to be bothered by that, because later on in the course, we will prove that. we'll prove that carefully, and you'll get to see it. So it's clear that alpha and beta are not homotopic to each other. So the equivalence, so you would say the equivalence class, the homotopy class of alpha, will not be equal to the homotopy class of beta. They're two different homotopy classes. And what's interesting is that every loop, because so you have to understand that an actual loop, closed loop on the torus, can be quite complicated. This is P. It can do all sorts of things. Maybe it kind of goes around like this, and then maybe it kind of returns back to P. So this is some general loop F. So something like that. And what's interesting about the torus is this. There's a surprising relationship. Namely, that alpha beta is equal to beta alpha. Now you have to understand what this means. This means if you go alpha first and then you follow it through by beta, that would be homotopic to doing beta first and then getting alpha. Now the reason why this is very surprising has to do with this. If you draw alpha on the torus like this, and then you draw beta separately, then we just said that alpha and beta are not homotopic to each other. So there's no way to homotope this one into that one. However, if you do alpha, so it seems like are we not contradicting what we said? So here's the part which is the reason why you're allowed to do that. The reason why you're allowed to do that is basically has to do with this. Because if you have a loop going like this, you're not allowed to open up the loop. You're breaking the loop apart. This is no good, right? This is not allowed. However, if you have a loop going like this and you have a loop going like this, look at what you're allowed to do. You're allowed to open them up. Because by opening them up, it stays a closed loop. This is still a closed loop. That's the whole idea. That individually, you're not allowed to open up alpha because you're breaking the loop, right? You're violating the homotopy requirement. But when you have them going together, you see, if this is your base point P, that's no longer your base point P. If that is your base point P, by moving them apart, you can still keep that as your base point P. And the picture is, now I'm not able to draw it, but I can send you a video to show you how this goes. That by doing this kind of process, when you separate them like this, you can then move them around this ring of the torus and interchange it in the way so that the red one, you see, we're saying red one goes first, blue one goes second. And you can interchange them so that the blue one will go around the inner ring and the red one will go around the outer ring. So if you find this, like I know what some of you might be thinking. You might be thinking to yourself, there is no way that I would have ever realized this. How would I ever succeed in topology? So fortunately, the whole point of algebraic topology is to let the algebra do these things for you. The algebra, you let the algebra speak for itself. It will do these things for you. So it's not something that you have to necessarily visualize to get the right answer. You'll be able to use various rules that we develop to get this kind of result. So I want to show you a nice video that will kind of illustrates what I'm trying to say here. So let me bring this up for you so you get to see it. Something I cannot draw. So let's look at this. So here is, in this video, they're going to take that square. This is if you've never seen this before, this is like the common way you get a torus. I'm going to take that unit square or rectangle. You're going to glue the edges together. Okay, so there's our torus. Now, those are the two, so they're showing you the two loops. So let me do it like, I'm going to keep the mouse on the inner one, okay? So notice my cursor is on the inner loop. I keep it on the inner loop. I'm still keeping it on the inner loop. And there it is. It's on the outside. And notice, you see, that's the whole point. You're allowed to separate them because the base point stays where it should be. So that's like a very nice illustration of that. So anyway, so this is the surprising relationship that exists. And the fundamental group of the torus, we said it's two copies of the integers. So it's sort of similar to a circle. You're going to count how many times it winds around the inner radius and the outer radius. So the way the fundamental group will look like, you will have, of course, it will be a set. You will contain the constant path at P. Then you will have alpha. You will have beta. Then you will have alpha squared. You will have beta squared. So alpha squared is just a path that winds around the inner radius twice. Then you would have alpha times beta. But you're not going to write beta times alpha, then, because that would be the same thing. That this is the same thing as beta times alpha because of this relationship down here. Maybe I should not use brackets. Maybe the alpha should just represent the whole equivalence. Yeah, so maybe I should just write it like this. You have the identity, which is 1. We just normally call the identity 1. So 1 here does not represent the number 1. That's just the identity homotopy class. We said you have an alpha, you have a beta, alpha squared, alpha beta. Beta alpha is the same thing. So in general, this is the way it's going to look like. It's going to be alpha raised to the n, beta raised to the m, where n and m are integers. So that's the way it's going to look like. Because since alpha and beta commute, you can always put the alpha first and the beta second. So you can see you're getting two copies of the integers. You have an integer for alpha and you have another integer for the beta factor. And it's essentially like the winding number thing. Like if you look at this path f, how would you express f in terms of alpha and beta? So the f from the picture, it goes around one time around the larger radius. So that just would be beta, just one copy of beta. It will depend on the orientation. So you can see it follows the same orientation. And then the orientation on the alpha, it's to go like this. So this one is going around. How many times does it wind around? So that would be 1 time, 2, 3, 4, 5. I guess it's 5 times. So you would have beta times alpha to the 5th. And because it's commutative, you can write it like this. So that's the way you can express this particular homotopy class. So actually, maybe I should say that the homotopy class, the homotopy class of that entire loop is equal to this. So that's the way you can express it. So that's the reason why the fundamental group of the torus is isomorphic to two copies of the integers. Now, sometimes the fundamental group is not an abelian group. In other words, it does not satisfy these commutative relationships. So that's the other one that I wanted to show you. And that's going to be our last example. So here X, this is the figure 8 space. And the notation that we use is we write S1V S1. So this just means that X is a circle, and it's a circle, and they're both joined at a point. Naturally, you're going to call that as your base point, even though it really does not matter which one you use. And we're going to talk about the fundamental group of X at P. So this one is, so this is the notation. This is Z star Z. This is called the free product. This one is also sometimes called the coproduct. So it's basically like Z times Z, but not commutative. So as we draw the pictures, this will make sense. And again, as I said, as the semester goes on, we'll be able to prove these results. So you just have to wait until we develop the machinery to prove it. We do prove it in the other topology course by using different methods, but in this class we'll use alternative methods to get these results. But basically, the way this is going to work is you're going to have, that's your base point P. So you're going to have a loop. One of them is going to go like this. Let's call this alpha. And the other one is going to go like this. Let's call this one beta. And I think it's intuitively clear that alpha and beta are different homotopy classes. There's no way to move the blue one to the red one because you have all that empty space. So it makes sense why you cannot move that one over to the other side. So that makes sense. But unlike the torus, but furthermore, alpha beta is not equal to beta alpha, because alpha beta is supposed to represent going around alpha and then going around beta. And if you do this first and then that second, you cannot do this one first followed by that one second. There's no, basically what we're saying, there is no homotopy to convert that picture to that picture. Because with the torus, you were able to sort of open that up and then wrap it around the other side, but there is no other side and you cannot open it up. It's just a single point. You cannot separate them at that point anymore. So again, it's not rigorous, but intuitively it makes sense that there's not much you can do, you can really do about this. So this is the free product. So it is free from any relationships. There's no relationships. For example, if you have two elements and they commute with respect to each other, alpha, beta, beta, alpha, if they commute, that's called a relationship that exists between the elements. So it's free. It has no relationships, none whatsoever. So if you actually write this out as a group, this is the way it's going to go. You have the identity, you have alpha, you have the inverse, you have beta inverse, then you have alpha, beta, but beta, alpha, that's different. It's free. That's why it's called free product. So you're kind of taking like two copies of Z, but it's free from any relationship. So you have to treat these as different. And then you have alpha squared, beta squared. Then you can have alpha, beta, beta, and so on. You can have alpha squared, beta, -3, and so on. All of these are different. So essentially, so basically, it is the group of all words using alpha and beta. And once you write down a word, there's no other way you can write down a word. That's why it's called free. So if you've never seen this before, the name of this group, this is called the free group of rank 2. So that's how it's called, free group of rank 2. So we gave several examples. So we said convex spaces, trivial group. The spheres from dimension 2 and on are also trivial groups, though they're not convex anymore. The circle, fundamental group of the circle, the one-dimensional sphere, that's isomorphic to the integers. The fundamental group of the torus, that's two copies of the integers, but they commute. And then the fundamental group of the figure 8 space. So again, two copies of the integers, but they do not commute. That's why we call it a free product. There's no relationship on the loop that goes around this one and the loop that goes around that one. So that's just an overview of the fundamental group. I imagine that many of you have seen this before, and this is the reason why there was like a lot of information in this one lecture. But I want to get the fundamental group out of the way so that we all know what it is for the sake of completeness. And then we're going to move on to a topic that will probably be new for all of you.